All right, so thank you for coming to this talk on machine learning in the browser. So my name is Athan Reines. I work full-time on an open source project called StandardLib, which provides a standard library for JavaScript and Node.js with a focus on numerical and scientific computing applications, which also includes machine learning. So the talk overview is as follows. First, I'll motivate why machine learning in browser environments is important and why you should care. Next, as this talk concerns machine learning in the browser, I will discuss JavaScript as it relates to machine learning. Then I'll walk through some browser-based machine learning examples. I'll then highlight a few promising libraries and frameworks for browser-based machine learning. Next, I'll discuss what is happening at the standards level, which is making the web platform a better environment for machine learning. Then I'll offer some tips and tricks. And finally, I'll offer some conclusions and additional resources you can use to get up and running. Now, if I move too quickly, this entire talk is online with notes, so you can review it both during and after the conference. You can simply go to my GitHub page or follow me on Twitter, where I'll tweet out a link. So just so I can get a little bit of a feel for the room, I'm guessing all of us are machine learning practitioners? More or less? No. Okay, that's fine. How many of us have used or have done machine learning in browser environments? Anyone? No one? Okay, so this is like, what are the cool kids doing kind of talk. Okay, got it. All right, so for those in which there's like technical jargon or whatever else, I'm not going to go into like what is machine learning, what's a model, etc. However, in the appendix of this talk, in the notes, you can find various explanation of technical terms, etc., and a more gentle introduction to machine learning. For the purpose of this talk, I'm just going to kind of assume that we all know what machine learning is and what we can use it for. So why is machine learning in the browser exciting? Running machine learning algorithms in the browser allows for localized model training and prediction/classification. And I don't need to decouple these two aspects, the training and the prediction. Meaning in practice, for particular types of problems, I do not need dedicated infrastructure or processes/threads for training and separate infrastructure for the prediction. So not only does this stand in contrast to traditional kind of big data architectures that we kind of think about, but this also stands in notable contrast to environments such as Jupyter notebooks, which effectively make the browser a glorified RPC client and require a backend server architecture to actually receive and execute commands. So I'm guessing many of us have used Jupyter notebooks or some type of notebook environment, right? Databricks, etc. Now, why is this distinction important? And it's important for the following reasons. The first is privacy. Running machine learning algorithms in browser environments allows data to stay on device. For example, for health and fitness trackers, such as the Apple Watch, they now have APIs which allow you to access heartbeat data. Now, by running incremental machine learning algorithms on device, I can train a model, for example, learn a user's normal heartbeat pattern, and then detect when a heartbeat or a set of heartbeats no longer fits this pattern. In this scenario, I never have to send data off to some remote server. All data can stay on device. And with browser environments, in particular JavaScript, you can deploy web applications in pretty much any environment anymore, whether that's on IoT devices, whether that's on smartwatches, whether that's in web browser or desktop applications, etc. A browser environment truly is very portable around the different ecosystems. So if you really care about portability, a browser environment is a very good target for deploying machine learning applications. Now, because I don't need to send data to remote servers, analysis has low latency, it works offline, and it can be more power efficient. And then finally, as analysis can occur on device or using newer kind of buzzword technology, terminology at the edge, we can have direct access to device sensor data through traditional web APIs, which removes the need for often complex device data serialization and deserialization logic. Now, to help motivate machine learning use cases, let's consider some real-world data sets that we might see in a browser environment. Now, in browser environments, we have like data streams such as mouse and cursor movements, scrolling, clicks, And with modern web APIs, we have access to sensor data such as device orientation, temperature, ambient lighting, all data of which is being continuously collected. And then finally, we have monitoring data such as logs of failed HTTP, HTTPS requests, application errors, etc. Like many of the things that you might encounter in a server environment. Now, what can machine learning and browser environments allow you to do? The short answer is most everything that you can do in non-browser environments. The main exception being the batch analysis of data of sufficient scale that's impractical for a single device. And as particularly concerns browser environments, for the UI interaction data we discussed in the previous slide, such as cursor movement and scrolling, we can generate a prediction as to what resource a user is most likely to want next, allowing us to create what would feel like a more responsive and faster UI. Now, one example I've seen in kind of like a real-world application is where the application tracked a user's XY cursor coordinates, and then built a model, and then based on where they thought the user was going to click next, like what button, they would basically mimic or simulate the clicking of that button just before a user did, and then send off a request, get the resource, such that it feel like an immediate experience, right? And as we all know, like running like e-commerce things, like somehow milliseconds matter in all of this. Another classic use case, if we're familiar with machine learning, is anomaly detection, such as detecting a malfunctioning system or fraudulent activity, where that's failed password entering attempts or etc. And in this classification task, what we want to do is we want to detect when a datum or a set of datums is different than the rest. And of course, the sooner we're able to classify data as anomalous, the sooner we can fix a potential problem. And then a third use case, also traditionally in machine learning, is clustering, which is the process of assigning groups. Now, as an example, we could collect device performance metrics and identify, hopefully, different application states, such as resource intensive or idle, etc. And then based on the number of states and how frequently they are occupied, this could be informative for like on-device resource planning and optimization. Now, at this point, we should probably ask, okay, well, you know, you've converted me, machine learning is important, that's cool. But why do any of this in JavaScript? Why do any of this in browser environments? And in particular, like, don't other languages exist which are better suited to the task? And don't the advantages of those other languages outweigh any potential benefits of running machine learning algorithms in browser environments? Now, as a practitioner who has written and used machine learning algorithms in other languages, I can confidently say that JavaScript is perfectly suitable for running machine learning algorithms in browser environments, and it's just as equivalent as R and Python is for running machine learning algorithms and doing mathematical computation. However, the stigma that JavaScript is somehow not suitable for math and by association machine learning persists, so I'd like to take a moment and dispel a couple of myths. The first myth is poor performance. And as part of our work on standard lib, we have written and run the benchmarks, and you can run them yourself, they're publicly available. And JavaScript environments are just as fast as, and more often not faster than, Python, and certainly faster than R. And why is this? Now, modern JavaScript environments are highly optimized. They're continuously improving just because of the constraints of the system. Now, with WebAssembly and Node.js native add-ons, achieving near native speed in JavaScript environments is actually readily achievable. And the second myth is that JavaScript is somehow incompatible with mathematical computation. Now, the argument in support of this myth typically goes something like single-threaded, something, something, floating point, something, something, 64-bit integers. And what is clear about the people making this kind of argument is that they have not used other languages for scientific computing or machine learning, because many of those arguments that are used against JavaScript apply equally well to those other environments. And people can, and more importantly, do write robust and performant mathematical code in JavaScript. And personally, I can point to standard lib and the fact that we've written literally thousands of mathematical functions, and never once has we encountered any overwhelming issues due to the language itself. Now, this said, yes, some languages do offer more convenient syntax, like terser syntax, like if you use your MATLAB or you use Mathematica, or even in Python with operator overloading. However, the lack of these features does not preclude writing mathematical algorithms in JavaScript and running them in browser environments. You know, in short, many of those who who say you can't run these algorithms in JavaScript seem to have various preconceptions which are not grounded in reality and most likely have never written mathematical libraries. For instance, the operator overloading limitation exists also in C, but no one who seems to think that JavaScript is not suitable for mathematical computation seems to think the same thing about C. The primary reason why people do not write mathematical intensive algorithms in JavaScript and by association in browser environments is that other ecosystems already have a critical mass of libraries and frameworks for doing mathematical computation. The issue is not one of technical limitations, but one of community support. And this is a problem which myself and other people are actively working to address. Now, to help dispel the aforementioned myths, let's turn to some examples demonstrating machine learning in JavaScript, and not just any machine learning, but real-time machine learning, because you take real-time machine learning and you get an amazing buzz phrase that marketers love. So the first example is real-time anomaly detection. And to help structure this example, what I've done is I've created an interactive observable notebook similar to a Jupyter notebook, which steps through the analysis of the sensor data. So that notebook is here, which is also publicly available. So don't worry about getting all the code snippets. I'll tweet out links to all of this so that you can actually see the analysis. But the basic idea is we have some sensor data and we want to be able to develop an anomaly detection algorithm. And how we're going to do that is we're going to use Grubb's test, which is a statistical hypothesis test, which tries to detect outliers in a univariate data set that's assumed to be normally distributed. The basic idea behind Grubb's test is it wants to try to figure out, is the minimum or maximum value an outlier? That's the basic idea. Does a data set, a univariate data set, have an outlier in it? That's it. So, in order to run this analysis, and all this analysis is happening on the client, in the web browser, no servers involved, etc., except to send off the web application. The first thing I do is I load this particular library. This is standard lib. For the next couple of examples, we'll be working with standard lib. I'll show some others later in the talk. We also load in the data set that we're going to use to analyze. We define some statistical accumulators. This is for like computing running means and standard deviations. We then define an accumulator for performing Grubb's test. This is going to be our outlier detection component. We then need to define some utilities for determining data normality, as well as creating linear spaced arrays, just like you might find in NumPy. And then finally, we have a plot API that we're going to use for plotting data. So in this analysis, being the good practitioners that we are, we need to do some exploratory data analysis, which means loading that data set, defining some utility functions. In this case, all this function does is it says for a particular moat ID, in particular this data set is a sensor network, a very simple one in which you have different moats or sensors. So here what we're doing is we say, give me a moat ID. This could be a number 1, 2, 3, 4, and then a particular key. This is a feature, such as temperature or humidity, and we're going to generate that data series. This is just your typical data munging task. We can use that to extract out various moat readings for temperature, and if we generate a plot, we see that for moat 1, we have some kind of baseline behavior, and then around reading 2200, we have a large spike. Maybe this is an anomaly, maybe this is not, but we should probably look at other moats to see what's going on. So we can do this for moat 2, and with moat 2, what we can see is that we have the baseline behavior similar that we saw in moat 1, but with the absence of any major event. Okay? So maybe that was an anomalous event, and we would like to be able to detect that. I should note that in this notebook, we're using a static data set, but everything that's done in here, the analysis is equally applicable to real-time analysis using accumulators. So one thing we should determine before we can apply Grubb's test is where this data is normally distributed. And if we were to kind of take a closer look at that data set, we'd see that that data is non-stationary. And by non-stationary, we mean that the statistical properties change over time. And it's clearly not normally distributed. But we should probably go ahead and try to statistically verify this. And how we do that is using the KS test. In order to do that, we compute some statistical quantities. We then perform that test. And what we end up seeing is that we reject the null in favor of the alternative, meaning that this data on a global scale is not normally distributed according to this test. Now, we could hypothesize that maybe the data is not normally distributed over long time scales, but maybe it's normally distributed on short time scales. So we could think for an anomaly detection algorithm, what if we created like a sliding window algorithm in which we could apply Grubbs test to small windows as the data set comes in. So in order to kind of help motivate that, what we'll do is we'll smooth the data out using a smoothing function, a running mean. And of course, by smoothing, that means we reduce reading to reading variability while still hopefully preserving the larger features in the signal. Once we've done that, we smooth it, we see that we do reduce that reading to reading variability while still preserving the non-stationarity of the signal. Once we've done that, we can now try to test our hypothesis that while not globally normally distributed, we can think about it as locally normally distributed. So we create a KS test that runs a moving KS test along the data set. And in order to help us determine the best window size for evaluating normality, we can run analysis in which we plot window size versus the number of windows which fail normality. And what we end up seeing is that the kind of optimal window size for normality in this case is around 20. As you increase the window size, we see that we have more windows which fail normality, which accords with intuition, because the longer your time scale, the more likely that you have non-stationarity in your data set. So we're going to go with a window of 20. And now we can actually develop our outlier detection algorithm. And we use Grubbs test in order to do this, in which we evaluate Grubbs test over the windows as we slide them along. And then we define a certain significance level that allows us to kind of tune the sensitivity of this algorithm. So we're going to apply this anomaly detection algorithm to the second mote, which we can use as our control in the absence of large-scale anomalies. And what we end up finding is that it doesn't seem to find any anomalies, which is okay. But we'd also like to know, will it actually work on our data set, which seems to have an anomaly? So we run the same kind of analysis on mote 1 data. We see that fails the global normality test, which is to be expected. We smooth the data, and then we perform the local KS test to test for normality. And what we end up finding is that we end up getting more windows which fail normality. So we might think, okay, maybe there's a possibility for increased outliers in this data set. And then when we actually apply the outlier analysis, lo and behold, we're able to detect this particular outlier, which is great. Of course, you might say, well, this is you probably tuned this, etc. Well, you can apply this to other sensor network data as well. Now, the main takeaways from this is that we just did an entire analysis kind of dispelling the myth that you can't do this in browser environments or using JavaScript or web technologies, right? All of this analysis, KS test, statistical hypothesis testing, all the machine learning, data munging, et cetera, happened entirely within a client environment. So you could easily deploy this similar type of analysis in your web applications as you deploy them. All right. So the next example is going to be real-time clustering. And basically similar to the previous example, I've created another notebook that you can do interactive analysis. In this case, we're going to try to do real-time k-means clustering. We're going to use simulated data, as this allows us to control data generation and also allows us to know the true underlying state of the system. But you can equally apply this data to real data. So just kind of like walk through this again. We load some libraries. We load some random number generators for generating synthetic data. We then have a n-dimensional array data structure. So if you're familiar with like NumPy ND arrays, there's basically a JavaScript equivalent for creating n-dimensional data structures. Convenience functions for creating vectors and matrices. Plot, and then finally, the main substance of this notebook is going to be an accumulator performing incremental or real-time k-means clustering. So in order to generate our synthetic two-dimensional data set, there's some simulation functions, not particularly important. What is important, the main idea behind this is that the data that we're going to create is a discrete time hidden Markov chain. So you have a Markov chain that goes through various transition states, and then based on that transition state, it emits a certain observation, which is corrupted by noise. And in this case, it's Gaussian white noise. So we define our simulator, which allows us to kind of like generate data in real time or mock that. And if we were to like kind of like look at the system, well, let me go back. We can define various Markov chain properties, such as the initial transition probabilities, the transition probability matrix, means, sigmas, which this is controlling the noise that we'd see in the observations compared to the underlying signal. Now, what we can do is we can actually generate this data. And when we generate this data and we generate a time series plot, it looks something like this, right? So we basically have a two-dimensional data set that undergoes various state transitions, right? It goes from like high to low, and there's some correlation between the two of them. If we were to turn this into a two-dimensional scatter plot, it would look something like this. And what we can see from this plot is that we have two larger blobs that may have some underlying structure within those blobs. And to kind of like help us see this underlying structure, we have the advantage of using a synthetic data set. So we can actually color code the generated data, and it looks like this. So from this plot, we see that we have what seem to be 5 different states, or 5 different blobs, clusters, which overlap. And our goal in writing this analysis is to try to resolve those individual blobs, or the underlying centroids. So in order to cluster the simulated data, we first initialize our accumulator for performing incremental k-means clustering. And then once we've initialized that, we're going to perform k-means plus plus initialization. We're going to seed it in order to be able to do reproducible analysis. Once we have that and we generate a synthetic data, the main thing that we need to see here is that this is like the main function which updates our accumulator, meaning this is what's going to instruct our k-means accumulator to incrementally update its underlying model. And to plot that simulated data along with the clusters, it looks like something like this. And what we see from this analysis is that those orange streaks are the algorithm trying to figure out where the underlying centroids are located within the underlying data set. And what we see is that as more data is provided to this algorithm, the better it's able to kind of like figure out those centroids. This is not the best initialization, given that there's some uncertainty in the larger blob up to the left. But if you to rerun this and probably give it slightly more data, it would probably be able to better resolve these things. But we can even do better in this. We can actually do this in real time. We can define an analysis class for managing the simulation state, as well as the analysis and the rendering of plots. And then what we can do is we can run the simulation. We can run the simulation. Or not. Or don't run. Fingers crossed. Okay, we'll give it a second. Maybe not. Okay, one more time. Oh, I know why. I should probably read my own comments. I need to do this, and I need to do this. Okay, now this will work. Okay, so now we're going to simulate the data. We have our simulated evolution of our system as it goes through various states. And then as data comes in through k-means plus plus initialization, we have a pretty good approximation where those initial centers are. And then here we actually see the algorithm learning where those centroids are located in real time, right? Which is, I think, pretty cool. Because what's nice about this, about being able to do this all client-side and be able to take advantage of web technologies, is the fact that we have a tight coupling between the visualization and the actual analysis of that data. So we have a tight feedback loop which allows us to kind of like probe and better understand what's happening at a fundamental level with these algorithms. And this is important. With web technologies, you can tighten kind of the pedagogical feedback loop in order to better understand what's actually happening with the algorithms that you run. As in this case, in which we can better understand how k-means clustering is working in real time. In fact, we can kind of change it. We can use like Fogey's initial algorithm, initialization algorithm, or random sampling, etc. And we can see how those initialization techniques may affect our ability to resolve the underlying clusters. Okay, let me just comment that out. Okay. All right. So a third example that we're going to do in the paradigm of real-time machine learning is real-time regression. So once again, we have a observable notebook. We do the same kind of preamble, loading in the library, as well as the data set. In this case, what we're going to use like the Boston house prices data set, which is a canonical data set that many people use for regression and prediction. And this time, how we're going to do the analysis is we're going to use stochastic gradient descent, but an online implementation. So to begin our analysis, if it scrolls, there we go. We just need to do some exploratory data analysis, just kind of getting a feel for the data. In particular, there's things like the average number of rooms per home, and then there's the corrected median house prices. If we were to plot this data set, we would see it looks something like this, which seems to have a fairly strong linear relationship. We can generate a plot matrix, which kind of like looks at all the different combinations, like so. Kind of like look through these. I can already say, having done this analysis, the average rooms per dwelling and the median house price seems to have one of the strongest relationships, so we're going to kind of use that for the rest of the analysis. And that's the kind of the goal here, is to try to take a feature and be able to accurately predict house prices. So currently it's rendering because I refreshed. There we go. All right. Now, in order to perform some real-time regression, we need to do some feature scaling and unscaling. This is what the standardization and inverse standardization functions do. We have another function for controlling simulation state of the real-time of the data set. And then once we do that, we can actually simulate the data. And then perform real-time regression analysis. And what we see here is as we feed it more data, the algorithm is trying to figure out the best model coefficients in real time. Now, just as in the previous example, in which there's kind of like a pedagogical like lesson behind it, in which you kind of like interact and play around with parameters and see these things update in real time. The same thing with stochastic gradient descent. So when you look at the scikit-learn documentation, etc., you often see that they recommend certain number of samples. I think in scikit-learn, it's like stochastic gradient descent is great for larger data sets of 10,000 or more random samples. And you're like, okay, good. And that's one thing to know that, right? And just to kind of like blindly apply that. But it's also another thing to actually understand that. And so what we can actually see here is that for low data sets, for smaller data sets, the issue with this algorithm is that it's very hard to achieve convergence. It's unstable. And that's why we often see the line kind of like flipping around, etc. But over time, as you give it more data, you're able to see that the line's movement slowly stops moving, and you'll actually get convergence. So if we were to divide this data up to like around, I think, 2,000 or 3,000 elements, we would see that the line would stop shifting, right? And just be able to see that visual feedback gives you a better intuition of how an algorithm works as well as its limitations in terms of why you shouldn't feed it only 500 data points as in the Boston housing data set, but rather you need much larger data sets in order to make sure that you get convergence. Or you need to develop other techniques in order to do this effectively. Okay. I'll go ahead and just close that one. All right. So there's a fourth example, which is real-time classification, but I'm not going to go through that. It's very similar to the real-time regression. If you're interested in it, just check out the standard lib repository. We can see examples. So at this point, I want to highlight various libraries and frameworks for browser-based machine learning. We've already seen one such library, and that's StandardLib, a project of which I am part, but there are others worth noting. The first is Observable, which you've already seen through those notebooks. Observable provides a interactive notebook environment, which allows you to interleave prose and code, aiding exploration and analysis. If you've used Jupyter notebooks, you kind of get a feel for what an observable notebook is all about. So to kind of like showcase a few examples, the first is we can just kind of like look at this one, which is domain coloring of complex functions. I'm not going to go into too much detail on these, but basically the author of this is trying to provide an explorable explanation in terms of the various techniques that you can use to visualize complex functions, creating very pretty graphs in the meantime. So he goes through the motivation, he gives equations, talks about the various techniques, etc. Now, the nice thing about this particular notebook, in contrast to something like Jupyter, is that the author is able to freely use all the technologies associated with the web platform. And in this case, the author showcases actually how to use WebGL, interleaving like various shader code into it. And that's another important thing about doing browser-based analysis, is especially like in an environment like Observable, is there's a creative coding aspect to it that may be a bit more missing or a bit more limited in an environment like Jupyter. Another example is a notebook called Routes to Chaos. And in this particular notebook, the author is exploring how to reason about and model chaotic systems. And again, similar to other notebooks, we have a mix of prose and code, coupled with some interactivity, allowing you to kind of like explore how a reader can better understand what is chaos and also how we can reason about it. These are just kind of like illustrative things to show that people are working on this kind of like space and doing these type of analyses in the browser. All right. And then another one is on the federal budget. So what this author is trying to do is to help the reader better understand the U.S. federal budget, and particularly as it relates to you. Like, if we were to take the U.S. federal budget, shrink it down, and it was your monthly income, how much of your monthly income would be allocated to various expenditures, such as defense spending or entitlement spending, healthcare, food assistance, etc. We've seen a lot of these different things, especially like in Europe. There's a lot of different like web applications that have explored this idea. But just to kind of go along with that theme, it's an interactive notebook along the lines of, if you're familiar with Brett Victor's work, Explorable Explanations, of interleaving interactive elements to allow the reader to better understand and adjust things and tweak things and update visuals to get a better, true sense of what's happening. And when we do that, we can play around with different things like Social Security or Medicaid, etc. And you get that based on your budget of around $6,000 a month, which is kind of the median U.S. Monthly budget, your allocation for health would be around like $64. Now, one of the advantages of Observable when compared to other notebook environments such as Jupyter is that Observable is what's called a reactive environment. And what this means is that instead of supporting out-of-order execution, what it ends up having is it has an underlying dependency graph in which when you update one particular cell, it updates all other dependencies within that graph, which is interesting because that means you can create more interactive applications, just like you might with a traditional web application. And because you can do this, it allows for a tighter integration between analysis and exploration and also creative coding. And that tighter integration, just to reiterate this, allows developers and analysts to more powerfully and expressively probe and interact with both their data and the algorithms which operate on that data. Okay, so that ends my promoting observable notebooks. Another library I want to talk about is TensorFlow.js. It's a machine learning library being actively developed by a team within Google Brain. So it is supported by Google. How many people have used TensorFlow? A couple of you? Good. So what TensorFlow.js aims to do is it aims to bring the power of TensorFlow to JavaScript environments, allowing you to train and deploy machine learning models in web browsers and Node.js. So we can actually run through a couple of examples, and I'm going to hope that these work. This is probably one of the more demo-intensive talks I've done. So has anyone seen these? You have. Okay. It's too bad. It's not going to be a surprise to you. So the first one is playing Pac-Man. So the goal of this demo is that I don't want to play Pac-Man with my hands. I want to play it by giving gestures based on up, down, my facial expressions, right? So how I can do that is I need to train a model. I can't actually see this, so I'm just going to stare at the screen. So for going up, I'm going to tilt my head up, and I'm going to give it various images to train for moving up. Now for it to go right, I'm going to turn my head to the right. I'll give it various images to turn right. Okay, now I'll do it for going down. Okay, a little bit odd. And then finally, we're going to do left. Okay, now we're going to hope that this works. I don't know about the angle. I might have to actually stoop down. But we're going to train our model. Excellent. Now it looks like we're ready to play. And since I can't actually see the screen while I'm doing this will be fun. Let's do this. I'll turn it around like so. All right. I'm ready. Sort of. I can't see it, so I could, but then come on, turn left. Turn left. Turn left. Turn left. Okay, there we go. You guys get the idea, don't you? Right? We can see that it's trying to figure out what I'm doing. But this is pretty cool, right? I can do this just by training a model in the browser, and then I can play Pac-Man by convulsing. I don't know. I think this is cool. So that's one example. Excellent. If I was doing this earlier today in my hotel room, and if you have it like level, it works better. But here's the angle. I'm going to blame it on the angle, not because I'm bad at Pac-Man. All right. So a second example is PoseNet. Are people familiar with PoseNet? So in contrast to the previous example where we actually trained the model in the browser and then played Pac-Man, and this one, not very good lighting, but here what we're taking is a pre-trained model, the PoseNet model. We're loading it into the browser, and then based on the live webcam feed, we are using it to, in real time, identify various features. So if I look at it, it should identify my eyes, my nose, my ears. It gives my torso. Let's see if I can do this. If I step back, it gives my arms. Excellent. Hands. Okay. Once again, this is all happening on the client in terms of actually evaluating this algorithm, right? You don't actually have to send out to any remote server architecture, which is great. If we wanted to do this in kind of like a traditional Jupyter environment way, you need to have like a dedicated server environment in your cloud infrastructure, and then you need to provision a new server each time a new client logged on, et cetera, right? This would not be great. Here, we can push all that computation out to the edge to a user's computer and leverage all of their computing power.
Just a small question.
Yeah.
Is it actual JavaScript code, or is it like in the backend something like WebAssembly?
So it's a mixture. It's a mixture of JavaScript and actually WebGL. Yeah. In order to get performance advantages, TensorFlow.js, it tries to take advantage of the GPU. So it's a mixture. They also leverage a little bit of WebAssembly, but everything is using web technologies on the web platform.
And the previous demos you gave,
yep.
Is that pure JavaScript? Or?
Pure JavaScript.
Yeah. And guess performance-wise, you might run into issues if you have larger data sets.
Yes, I'll actually get to that in a few slides.
Sorry about that.
No, you're fine. That's exactly what I want, the anticipation. So another thing that's kind of like cool about this, I guess there's one more example that we can kind of like look at, which is, this is by another guy in the TensorFlow team. Is for people familiar with like baseball, that, you know, like the umpires like call balls and strikes based on the ball being in the strike zone. So here what we see is a neural network that's being trained on labeled baseball strike data. Now, as it's being trained, that neural network is learning the strike zone, which here is outlined by that black rectangle. And we can see as more data is fed to it, as you might expect, the better it learns where that strike zone is located. And then once it knows the location of that strike zone, the better predictions that it can make once you give it an unknown or unlabeled pitch. Now, again, all model training, in this case, all model training and evaluation happens entirely on the client. No servers are needed. And then another thing that's interesting about this is that neural networks are often treated like black boxes, right? Things which are hard to understand and they're hard to reason about. They just work. I tuned some parameters and like magic happened. But by moving machine learning away from traditional environments such as R and Python to the browser, we're able to kind of like tighten that feedback loop again to visualize how an algorithm and even a neural network, black box, so to speak, learns in real time. And it allows us to explore and probe, in a sense, how this particular algorithm, quote unquote, thinks. And thus, we should not underestimate the importance of browser-based machine learning as an important pedagogical device. So, let me get rid of this guy. All right. The last library I want to highlight is Apache Arrow. Has anyone used Apache Arrow? No. Okay. So I'm going to give you the definition straight from their documentation. Beware, there's a lot of jargon. So Apache Arrow specifies a standardized language-independent columnar memory format for flat and hierarchical data organized for efficient analytic operations on modern hardware. Okay, so one of the main goals of Apache Arrow is to provide a common data format that can be used across environments and languages, thus avoiding like data serialization and deserialization costs. Think about going from like an R data frame to a Pandas data frame. Like there's a cost associated with doing serialization and deserialization in order to interoperate between those two environments. So the basic idea behind Apache Arrow is to provide a common underlying data format that other people can create APIs on top of, right? So then you can more efficiently and more portably use code across different environments. So to demonstrate its use in the web browser, we can once again upload or launch a new observable notebook. In this case, we can use Apache Arrow. We load Chicago Crimes data set. This loads a few 100,000 records into the web browser. And then we can officially do various like map-reduce style operations, etc., as well as generate plots, etc. So I suppose one other thing I just want to kind of highlight with this is that maybe people are like unimpressed with like a few 100,000 records. So I should say a couple things. One is that often in exploratory data analysis, it's not practical or efficient to analyze an entire data set. Often what you want to analyze is a representative sample, which is some smaller subset. So often when we're doing analysis, we're working with smaller data sets, in which case browser environments are perfectly suitable. The other thing I want to mention is that in theory, browsers have access to basically half your hard drive. So you can analyze by taking advantage of browser technologies such as browser databases and stream APIs, upwards of several gigabytes of data all within the browser, which should be more than enough for a lot of your EDA type needs and also for understanding and using machine learning algorithms. Okay. All right. So now that we've discussed like libraries and frameworks for browser-based machine learning, I want to highlight some recent developments at the standards level, which is helping accelerate the development and evolution of machine learning on the web. One of the most publicized developments is WebAssembly. which builds on the collective efforts of basically the past 20 years. And browser vendors came together to achieve consensus on a binary format for the web. In short, WebAssembly is a portable compilation target for the web. And what it allows is it allows running languages other than JavaScript within browser environments. And more specifically, the current focus is the ability to run statically compiled languages such as C, C++, and Rust within browser environments. So modern compilers such as LLVM are comprised of two components. They're comprised of a front-end compiler and a back-end compiler. The front-end compiler takes your high-level language, such as C or C++, compiles it down to an intermediate representation, and then a back-end compiler takes that intermediate representation and compiles it to machine-specific code. So in this pipeline, where WebAssembly sits, and it's abbreviated WASM, is right after the intermediate representation. So what ends up happening is you take your higher-level language like C or C++, compile it to an intermediate representation. The back-end compiler compiles it to WebAssembly. WebAssembly is then shipped off to a browser environment, either over HTTP or by loading from the file system if you're doing this in Node.js. And the browser is then responsible for taking that WebAssembly code and translating it to machine-specific instructions. So one of the interesting things about WebAssembly is because of this kind of architecture, people will say, well, WebAssembly promises or pretends a future, like a true virtual machine, a purpose that the JVM could never fully fulfill. WebAssembly will do it. Maybe it will, maybe it won't. But what's nice about this is basically you can compile to WebAssembly and it'll just run everywhere there's a browser environment, no matter where that is. So WebAssembly has two formats. It has a binary encoding and a text format. So to begin with the text format, WebAssembly defines a standardized text format which encodes a WebAssembly module with all of its contained definitions in a way that's equivalent to the binary format. So as an example, here's a WebAssembly module which exports a single function, add, which adds two 32-bit integers and returns a 32-bit integer result. And then this text format, we see that it's similar to a Lisp. The text format, commonly referred to as WAT, uses S expressions for representing the program tree. Currently, WebAssembly only supports 4 value types, which are all numeric types, such as 32-bit integers, 32-bit single precision floating point numbers, 64-bit integers, and then double precision. Any other value type must be constructed by manually manipulating the raw memory. And in practice, what this means is copying to and from the module heap and using pointers. So now that we have a simple working example, the binary format. The binary format is a dense representation of a WebAssembly module. So as an example, here's that same WebAssembly module we saw in a text format, represented in binary format. If we convert the hex on the left to a string, which you can see on the right-hand side, we can see that the module is comprised of 6 different sections. You see there's like a preamble, a type, function, memory, export. There's a code section and then a name section. So within this binary encoding, this dense representation, you basically define a module or an implementation as a series of sections. And each section begins with a name followed by the number of bytes comprising that section and then the actual section contents. Linear memory access is accomplished with explicit store and load operators. WebAssembly comes with basic flow control constructs such as ifs, loops, and blocks. And then the current WebAssembly specification defines many operators and functions for data type conversion, truncation, reinterpretation, promotion, and demotion. Here I'm just showing the 32-bit operators. If you're interested in more of them, see the specification, there's a lot. So WebAssembly has several stated advantages. The first is that the binary format is compact, which means that fewer bytes must be sent across the network. And if there's fewer bytes sent across the network for your web applications, that means faster load times. Next, because the binary format is structured, it's comprised of a series of sections, and has a defined layout, module loaders, i.e. like browser environments which are taking these modules in, need to only perform a single pass in order to parse an encoded module into an AST in preparation for translating to machine code. And why that's important is that means that code that you send off to a browser can be instantiated faster than you can with JavaScript, which requires multiple different passes. And because WebAssembly is strongly typed, it means more efficient serialization, and again, fewer bytes sent across the network. And also because of this strongly typed nature of it, as well as its just how WebAssembly is specified, we can do ahead-of-time optimization that you can't do with JavaScript. So typically in dynamically compiled environments, such as the JavaScript runtime, what happens is that there's a certain compiler or a bit of technology which is monitoring the code for hot functions. Once a function is identified as hot, it gets sent off to an optimizing compiler, which makes kind of optimistic assumptions about input types and output types. And that optimized function hopefully runs a bit faster. However, if that optimized function receives some kind of unknown input, it gets put into a de-optimization loop, in which it goes off and gets de-optimized, and then it gets analyzed for further inputs and outputs, and then it goes back through the optimization cycle again. And if it keeps repeating this, it gets put in de-optimization quote-unquote hell. Now with WebAssembly, because we already know input and output value types, we can perform all these kind of optimizations ahead of time, which means as soon as your WebAssembly code arrives in the web browser, it can start running fast immediately. And then because WebAssembly is strongly typed, we can avoid those de-optimizing cycles, etc. And then because it's lower level, it means that we can more efficiently generate machine code instructions directly from the WebAssembly source compared to JavaScript. And another thing about WebAssembly is that it currently lacks a garbage collector. Now this has some advantages in the sense that it means that you need to manually manage memory, which is good because then you can specify when you want to clean up memory, such as when an application is idle, etc. But it also means that dynamically compiled languages which depend on a garbage collector, such as Python or R, cannot be currently compiled to WebAssembly and run in browser environments. You have to work with statically compiled languages. So if we combine all these advantages, WebAssembly promises for certain applications better performance compared to JavaScript. So to demonstrate the performance advantages, here's a BLAST function, so the basic linear algebra subroutines that underpin many numerical computing libraries. And what this BLAST function does is it computes the sum of absolute values over a strided array. Now, if we compile this to WebAssembly and run benchmarks, this is what we get. So on the left-hand side, we have the length of the strided array. Then we have JavaScript performance results, WebAssembly, a hardware-optimized native add-on, and then the relative perf between the native add-on and WebAssembly. So I should say that the native add-on, the native code has a slight advantage because it's working with hardware-optimized libraries. If you were to just do a vanilla C implementation of that BLAST function, you basically get equivalent performance result as WASM. So we can see that for shorter arrays, it's faster just to do analysis in JavaScript itself. However, as array length increases, we see that WebAssembly develops a significant performance advantage compared to JavaScript. And in particular, for larger arrays, we see about a 6x performance advantage. This is still much smaller than a hardware-optimized native add-on. And one of the lessons here is that in browser environments, and this includes Node.js, which is a JavaScript runtime, is that hardware-optimized libraries will always win. And so WebAssembly is not a panacea that will work in all cases. However, it can provide a performance boost in browser environments. So I hope that answers your performance question. So there are a couple other initiatives happening at the standards level that are aiding the evolution of machine learning on the web. One of them is BigInt, which provides arbitrary precision integers to web platforms similar to Python. Another one is value types, which is basically paving the cow path for operator overloading and custom numeric types that you might see like in Julia, etc., such as complex numbers. And this will hopefully allow for a more terse syntax for expressing mathematical operations over vectors, matrices, and n-dimensional arrays. Apparently, I don't know why this is up. We'll go away. Okay. Okay, so some tips and tricks. And the following tips are kind of like generally applicable regardless of whether a machine algorithm is written and used in JavaScript. The first tip, which is perhaps most applicable to JavaScript, is to avoid built-in mathematical functions, i.e. mathematical functions which are defined by the ECMAScript standard and part of JavaScript's built-in standard library. Now, for a variety of historical reasons, the built-in implementations are ill-defined in order to allow browser vendors some flexibility in making trade-offs between speed and accuracy. And they also commonly have bugs. Now, since one cannot specify the environment, the exact environment version in which browser-based machine learning libraries will run, i.e. your users could be running a whole gamut of different versions. They could be running in an ancient browser, or they could be running in the most recent browser with a whole different amount of variations in between. If you want to ensure reproducibility of even the most basic mathematical functions, you need to use community-written libraries, such as standardlib, that actually write these things and have a consistent implementation and actually are versioned. Second, the ecosystem for browser-based numerical and scientific computing libraries is in significant flux, where there's no clear winner. These things are being written all the time. And so in order to ensure that you use quality implementations, you cannot rely upon proxies for assessing library quality, such as like stars and downloads. In order to ensure that you use quality implementations, you need to actually read the source. Just trust me on this. Read the source, verify the implementations that you're using. Next is, while kind of true in general, but especially for machine learning, what makes algorithms performant are like two things. The first is using the right data structure. One such data structure is ND arrays, which are single segment contiguous blocks of memory, which allow for more efficient cache optimization. Another is, which is common for real-time machine learning algorithms. It's simple, a circular buffer. However, while the textbook definition is simple, you need to be very careful on how you implement this in JavaScript environments to avoid poor memory management. It's really insistent, isn't it? Jeez. And then another one is trees, is that certain machine learning algorithms require specialized tree data structures, one of them being like quantile approximation. And the other aspect that makes machine learning algorithms performant, of course, is using the right algorithm. And once again, where this is critical, another example is quantile approximation. Like a naive implementation would try to store all the data in memory, sort it, and then compute the quantiles. A better implementation, we would use an approximate method with a tunable level with a tunable error rate and a tree data structure in order to generate approximations for your quantiles rather than exactly. So in batch analysis, especially for one-off analyses, we can be okay with not using the best algorithm or the best data structure. However, especially in web applications and in real-time machine learning contexts, these two aspects are critical, and you can't forego these two things. So there are like 4 points I want you to remember from this talk. The first is that JavaScript is perfectly suitable for mathematical computation and machine learning. And not only is machine learning in JavaScript and browser environments possible, but doing so introduces new types of machine learning applications, as we saw in the TensorFlow.js demos or in application monitoring, etc., which offer better data privacy, better performance, and better resource utilization. So in the words of Brendan Eich, always bet on JavaScript. Second, machine learning algorithms, especially real-time machine learning algorithms, require using the right data structure, regardless of what language they're implemented in. Third, machine learning algorithms require using the right algorithm, of course. And last is to get involved, because people are building the future of machine learning in browser environments now. And we need people like you to continue making that future possible. And this means contributing to open source libraries, writing observable notebooks, showcasing the latest and greatest machine learning applications, and getting your companies to help sponsor, either with developer time or with funding, machine learning development for the web. So with that, thank you. If you are interested in learning more about this stuff, you can check out StandardLib or contact me on Twitter. I'll be more than happy to hook you up with resources. And I'll be around for questions during lunch, etc. So with that, thank you very much.